Hello everyone, I am Sandareka Wickramanayake from National University of Singapore. This is my thesis presentation and I welcome you all to this presentation. The title of my thesis is Explaining and Improving Deep Neural Networks via Concept-Based Explanations. And I was supervised by Professor Winnie Su and Professor Mongli Lee. Within the last decade, deep learning has touched almost every aspect of our life, from entertainment to retail to manufacturing to transportation and even safety-critical domains such as healthcare. This is mainly due to the impressive performance of deep learning models. However, despite the impressive performance and many applications, DNNs behave as black boxes. Users do not understand how these models make decisions or how they work. This is particularly problematic when a model makes wrong decisions, as due to the black box nature, it prevents us from troubleshooting and correcting them. Hence, it is imperative to explain the decisions made by DNNs. In this research, we explore using concept-based explanations to understand DNNs in computer vision, especially convolution neural networks. In contrast to indicating importance of individual input feature towards the decision, such as importance of each pixel in an image, concept-based explanations explain DNN decisions in terms of representations easily understandable to humans, such as superpixels or word phrases. Concept-based explanations are easy to understand. Even lay users can understand these explanations. However, the objective of explaining DNN is to increase the end user's trust on these models. Therefore, in addition to being easy to understand, these explanations should state concepts influencing the model decision precisely without leaving room for ambiguity. In other words, explanations should be descriptive. However, some of the existing explanations may not be descriptive. For example, consider these visualizations. They show us that it is the head of the bird that influenced the model decision. However, they do not tell us which aspect of the bird's head caused the classification. For example, whether it is the shape of the beak, color of the beak, or eye color, we do not know. In contrast, a linguistic explanation, such as this is a Laysan albatross because of its long, thick hooked bill and the dark shading on its face, provides specific details which are important for understanding the classification, especially when the variations among different classes are subtle. Another very important characteristic that explanations should have is being faithful to the underlying model. Explanations should reveal true reasons behind model decisions. There are two approaches to generate explanations rationalizing the decisions of DNNs. The first approach is to build the model in the standard way and develop the explaining mechanism afterwards. Such approaches are called post-hoc explanation method. The second method is to develop DNNs with intrinsic interpretability. In this case, the interpretability is inbuilt to the model and model can explain decisions by itself without need for post-hoc methods. In this thesis, we explore two approaches to generate descriptive and faithful concept-based explanations. In the first approach, we propose a post-hoc explanation method to generate faithful linguistic explanations. In the second approach, we develop an inherently interpretable image classifier that learns human understandable features and provide explanations in word phrases. Finally, we use explanations generated from these approaches or any other concept-based explanation method to improve classification accuracy of the underlying model. Now let's discuss the first research question we address in this research. It is how to generate post-hoc linguistic explanations to rationalize decisions of a CNN that reveal the concepts that truly influence the model decision. The proposed framework Flex was published in AAAI 2019, and the code is also publicly available for anyone interested. The contribution of our work is novel framework called FLEX, which generates linguistic explanations faithfully rationalizing classification decisions of a CNN. There are a couple of existing methods which adapt a neural captioning model to generate linguistic explanations by conditioning captioning model on the predicted class. However, the explanations generated by these methods may not be faithful to the underlying model. The reason could be that the existing method do not extract any information regarding the decision-relevant features that influence the model decision. Instead, they generate explanations directly conditioned on the class label. As a result, the same explanations can be generated for different images of the same class, even though in some images, some concepts are not visible. Further, existing frameworks implicitly assume that if a DNN and human arrives at the same decision, they use the same reasons. However, this is not always true. In the standard training process, a classification model is trained to minimize the classification loss. Therefore, to differentiate a certain class, the model can learn any discriminative concepts from the training images. Those concepts may not align with human rationale. For example, figure A shows an image of cardinal. The concept that human uses to differentiate this class of bird is its black cheek patch. To check whether the model also think in the same way, we compare model confidence values for the original image and also when we occlude different body parts of the bird. Here we occlude the black cheek patch of the bird and also the crown. We observe that the drop of confidence is greater when the crown was occluded than when the black cheek patch was occluded, indicating that model has based its decision more on the crown than black cheek patch, unlike human. Because of these possible differences between human reasoning and model reasoning, in order to generate faithful linguistic explanations, we need a mechanism to identify features that influence the model decision and map those decision features to words. As a solution, we propose a new framework called FLEX to generate explanations that align with the model reasoning. Instead of merely conditioning the explainer on the predicted class, we propose a mechanism to guide it to generate explanations with decision-relevant words. A novel way is proposed to automatically derive decision-relevant features from the model being explained and associate them to words. Given these decision-relevant words, we design a new training objective function which encourages the language generator to include decision-relevant concepts when generating explanations. Now let's move into details on how we identify decision-relevant features and associate them to words. First, let me briefly introduce CNNs here. A typical CNN is composed of two basic parts: feature extraction and classification. Feature extraction part includes several convolution layers and the classification part consists of fully connected layers. Convolution layers are made of convolution filters which extract features from the image. The output of a convolution filter is called a feature map. Let's discuss how we identify decision-relevant features. For explaining purposes, we consider a CNN-based classifier with 4 convolution layers. However, FLEX can be applied to any deep neural network. Given an image and its predicted class, we identify importance of each feature map from various convolution layers. For example, consider the feature map highlighted here. We calculate the gradient of the score for the predicted class with respect to each activation of the feature map and take the global average and consider it as the importance of the feature map towards the model decision. We sort feature maps according to their importance scores and select the minimum set of feature maps such that the cumulative importance is greater than some threshold. This process is repeated for each layer in the CNN, and we obtain the set of important feature maps for all the convolution layers. Next, we want to associate some word to each important visual feature such that the word best describes that visual feature. We achieve this by calculating the co-occurrence between each visual feature and the word. For each image, we note down the set of important visual features and nouns and adjectives available in its description. Then, considering the whole training dataset, we calculate co-occurrence between each visual feature and word using dice coefficient. The word with the highest co-occurrence is associated with that visual feature. For example, the word belly is associated with B42. Features at different layers represent concepts at different granularities. For example, a feature at the first layer of a CNN may represent the concept of beak, while a middle layer feature may represent the concept of thread. In order to generate coherent linguistic explanations, we start from the last convolution layer to get the top K features based on its importance scores and words associated to these features. These words associated to these important top K features indicate the concepts used by CNN in its decision. For each of these concepts, we obtain its finer granularity description by identifying the feature maps from the third layer that influence the selected feature map, as well as their associated words. We do this recursively until we reach the first convolution layer of the network. The union of all the words associated with the top K features from 4 layers forms the set of decision-relevant words. After deriving the decision-relevant word for an image, we calculate the relevance of each word in the word vocabulary with respect to each image. Finally, we calculate the relevance loss in terms of these relevance values and the predicted probability. Adding relevance loss makes sure that when the explainer predicts a decision-relevant word, it is given a smaller loss value, and hence it is encouraged to predict decision-relevant words. To evaluate our proposed approach, we conduct experiments using 2 datasets, CUB and MPII. Also, we compare our model with existing state-of-the-art explanation generator frameworks. Next, we want a metric to evaluate the faithfulness of generated explanations. We cannot use image captioning metrics such as BLEU, METEO, etc. because they do not capture whether the generated explanation contains the concepts that correspond to the true features used by the model. Here we propose a decision-relevant measure called DREL to determine how well the generated linguistic explanation describes the visual features used by the model. Given the fine-grained annotations for each image that describe objects in the image, we use saliency maps generated by GradCam to identify objects that are responsible for the model decision. DREL measures how many of the decision-relevant words are captured in the generated sentence. In this table, we show the results. We observe that our framework achieves the highest accuracy compared to VE and MME in both datasets, indicating that Flex can provide explanations with more decision-relevant words. Here, we show sample linguistic explanations generated by Flex, VE, MME for CUP. We use GradCam visualizations to highlight the regions used by the model for its decision. We observe that although the explanations generated by VE and MME describe different visual features in the image, they do not include objects in the highlighted region. indicating that these explanations do not reflect how the model makes its decision. Consider the bird classified as eared gray. The GradCam visualization shows that it is the long beak and red eye of the bird that influence the model decision. Plex is able to generate explanations, including those words, a red eye and a long flat beak, whereas the other method have failed. Another important benefit of explanations is understanding reasons for misclassifications. Correct explanation for a misclassification should describe common features between ground truth class and the predicted class. Because these common features may have caused the classifier to make wrong predictions. We consider that a generated explanation provides correct insights for a misclassified image if all the features mentioned in the explanation are common to both the predicted class and the ground truth class. Plex can provide correct insights for 70.5% of misclassified examples. In summary, in this work, we propose a novel framework to generate linguistic explanations faithfully rationalizing classification decisions of a CNN. We also propose a decision-relevant metric to evaluate faithfulness of explanations. The proposed framework can also provide insights for misclassifications. Next, let's move into second work, where we develop an inherently interpretable image classifier that learns human understandable features and provide explanations in word phrases. The research question we address in this work is how to develop a CNN that learns human understandable features and make interpretable decisions. The proposed model CCNN was published in IJCNN 2021. The contribution of this work is a new CNN-based image classifier that provides a prediction along with an explanation for a given image. Let's get back to the simple CNN we used earlier. Suppose we have a global pooling layer between the convolution layers and fully connected layers. Then we can interpret output of the global pooling layer as how strong a feature is present in the input image. For example, we can consider F1 as how strong V1 is present in the image. Further, a fully connected layer can be interpreted as a linear model. We can obtain an interpretable model out of CNN if its learned features are interpretable. The question is if a CNN that is trained on standard way can learn these interpretable features. Existing work has shown that the features learned by standard CNNs are not interpretable. As a solution, existing inherently interpretable CNN have come up with extra regularizations to learn interpretable features. For example, some force each convolution filter to be activated for a specific region of an object across all the images, whereas some method guide to learn prototypes. However, the features learned by these models are not consistent with human perception. For example, these two visualizations shows features learned by an existing inherently interpretable model. They either cover regions of multiple concepts such as bird's head and bird leg, or partial region of a concept such as tail. Ideally, for better understandability of a CNN, the features learned by a convolution filter should correspond to a concept that is consistent with human perception and can be described in a word phrase. In other words, we can tag the localized region corresponding to the learned feature with the word phrase consistent with human perception of that region. For example, this localized region can be tagged as orange beak and this localized region can tagged as black crown. In a CNN learns features that are A CNN learns features that are consistent with human perception, and a contribution of those features are linearly combined to make the classification decision. We call such CNNs comprehensible convolution neural networks. Such models allow us to generate faithful linguistic explanations. For example, a comprehensible CNN would explain that it classifies the bird in this image as American goldfinch due to the concept orange beak and black crown with their respective contributions of 0.9 and 0.1. Now let's discuss how we guide CCNN to learn such human understandable features. In this work, we introduce a concept layer into a CNN-based architecture, and we guide filters in this layer to learn human understandable features by learning the mapping between visual features and word phrases. For that, we have designed a new training objective function that considers concept uniqueness and mapping consistency. CCNN employs a global polling layer to express its classification decision as a weighted sum of its learned features. With this, we can explain the model decision in terms of word phrases and their corresponding contribution without need for a post-hoc method. In order to guide the CNN to learn human understandable features, first we identify the word phrases correspond to the discriminative concepts in the dataset. We assume that each image is accompanied by a description which describes the content of that image. For each class, we identify a set of word phrases describing the concepts of that class using the descriptions of the images of that class. We consider this set as documents and apply TF-IDF scores. For each class, the top R word phrases with the highest TF-IDF score are considered to be the word phrases describing discriminative concepts of that class. The union of all the identified words correspond to the set of concepts that the concept layer will learn. Suppose there are n phrases, then there will be n filters in the concept layer. Interpretability is enhanced when each filter in the concept layer is able to learn the visual feature corresponding to only one word phrase. For example, suppose filter 1 in the concept layer always activates for the concept background. That is, if the input image contains the concept background, it is activated, others it remains inactivated. Also, similarly, filter 2 always activates for the concept of orange beak, and filter 3 always activates for the concept yellow crown, and so on. We achieve this using concept uniqueness loss. The concept uniqueness loss penalizes the model if a filter is activated when its corresponding concept is not available in the image, or if the filter is inactivated when its corresponding concept is available in the image. However, in an image often contains multiple concepts, and a subset of these concepts co-occur, especially for the images of the same class. For example, most of the images from American goldfinch class have the concepts orange beak and black crown. Therefore, whenever the model see an image from these class, these two filters, filter 1 and filter 2, activate together. This makes it harder for the model to know which filter output should correspond to the word background and which filter output should correspond to the concept orange beak. We address this issue using mapping consistency loss. Mapping consistency loss has two components, semantic loss and counter loss. Semantic loss guides a filter to learn the correct mapping by enforcing similarity between the pair of visual feature and its corresponding word phrase to be higher than that between the visual feature and any other word in the embedding space. Further, for a filter to isolate some concept, we compare differences between an image that has the concept with an counter image that doesn't have the concept. For example, for the concept background, the image below can be considered as a counter image because it doesn't have the concept of background. For each concept that is in the input image and not in the counter image, the word phrases, corresponding to the feature should be more similar to the image visual feature coming from the input image than the visual feature coming from the counter image. This way, mapping consistency laws guide the filters to learn the correct mapping. Mapping consistency laws together with concept uniqueness laws make sure that CCNN learn comprehensible features. Next, let's move into the evaluation study. We use 4 datasets in our experiments and we compare our model with 3 existing inherently interpretable models. We compare these models in terms of classification accuracy and comprehensibility of the learned features. This table shows the comparison of classification accuracies of interpretable models. We observe that CCNN achieves the highest classification accuracy across all the datasets. Next, we evaluate comprehensibility of learned features. For that, we introduce 2 matrices, homogeneity and singleness. We calculate homogeneity and singleness per filter. The homogeneity evaluates if the filter activates for the same concept across multiple images. Singleness evaluates if the filter activates for a unique concept. For example, filter A has a higher homogeneity as well as higher singleness because it is activated for the same concept of red legs across multiple images, and in one image it is activated uniquely for the concept red leg, whereas filter B has a high singleness value because in each image it is activated for a unique concept. In this image it is activated for red legs, and in this image it is activated for white patch. However, it has a lower homogeneity value because in different images it is activated for different concepts. This graph shows the percentage of filters having different homogeneity and singleness values for each of the interpretable CNN. We observe that more than 80% of CCNN filters have homogeneity greater than 0.8, and more than 80% of CCNN filters have singleness values greater than 0.85. Next, for a qualitative evaluation, we visualize the features learned by filters in different CNNs. We observe that filter 484 of interp-CNN have a low singleness value of 0.73 because it is activated for the partial region of bird's head, bird's neck, and bird's back. Compared to interp-CNN, filter 25 in CAM has a low homogeneity value because in different images it is activated for different concepts. Compared to interp-CNN and CAM, ProtopNet has a higher homogeneity value and lower singleness value because the receptive fields of these filters covers multiple concepts. In contrast, CCNN filters are consistently activated by the unique concept across multiple images. Finally, we conduct a user study to evaluate the comprehensibility of learned concepts by CCNN compared to other models. We randomly select 40 images from subfamilies test set, and for each of these images, we visualize the most activated filter of each model for that image. The visualizations of each image are shown to the users and they are asked to rank the visualizations on a scale of 1 to 4, where 1 indicating the most comprehensible visualization that best localizes the body part. Results are given in this table. We observe that CCNN has achieved the highest rank, indicating that users find concepts learned by CCNN are more understandable. In summary, in this work, we propose a novel CNN-based classifier that learns features consistent with human perception and makes interpretable decisions. We also propose two matrices to measure comprehensibility of learned features that are homogeneity and singleness. Let's move into the final work of my thesis. In this work, I am using explanations from previously proposed works and also any other concept-based explanation method to improve the performance of the underlying model. The research question we address in this work is how to improve the prediction accuracy of a DNN using explanations of its decision. The proposed method BRACE was published in NeurIPS 2021. The contribution of this work is a framework called BRACE that utilizes concept-based explanations to automatically augment the dataset with new images covering underrepresented regions to improve the model performance. We know that machine learning models learn decision boundaries based on the training dataset. Ideally, the training dataset should provide sufficient variations in each class so that the model can learn the correct decision boundaries. As an example, consider the problem of classifying black terns and white-breasted nuthatch. Here we show some of the training data for both classes. In this case, the training dataset of black tern is not representative. Why? Because it contains only very few images of juvenile black terns. Juvenile black terns have white belly and breast in contrast to the adult black terns. When there are such underrepresented regions in the training dataset, the model may not learn the correct decision boundary, which then lead to make misclassifications of new data points. Consider a test image of juvenile black tern showing white breast and belly and black crown. Based on the decision boundary learned from the original dataset, this test image is misclassified as white-breasted nuthatch. Clearly, there is a need to augment the training data to include more images of juvenile black tern in order to learn the correct decision boundary between these two classes. A common data augmentation approach is to apply different transformations such as flipping, rotating, or zooming to training samples or to mix existing samples to create new images. However, such data augmentations only explore the neighborhood of the existing samples and may not cover the underrepresented regions. Another possible approach is to query an image resource such as Flickr or Google using the class name as the keyword and obtain images to augment the dataset. When we augment the training dataset with the images from underrepresented regions and retrain the model will learn the correct decision boundary between black terns and white-breasted nuthatch, leading to make the correct decision. However, this approach may introduce noise such as out-of-distribution images and degrade the classifier performance. For example, figure A shows the images we retrieved when we query a repository using the keyword black tern. You can see that this set contains images of juvenile black tern, adult black tern, and also some out-of-distribution images. Further, we should make sure that these added images are informative. We can use concept-based explanations to find such informative samples. As discussed before, explanations can provide insights into wrong classifications, revealing wrong or undesirable correlations that the model has learned and shortcomings of the dataset used to train the model. For example, when CCNN misclassifies the bird in the input image as white-breasted nuthatch, CCNN explains that the concepts white breast, black crown, and white belly cause the misclassification. Adding juvenile black terns that clearly showing these concepts will help the model to learn more generalizable features. For this purpose, we introduce a framework called BRACE, which utilizes concept-based explanations to identify candidate samples from image repositories for data augmentation. The key idea is to identify concepts that have led to misclassifications and augment the dataset with images that contain these concepts. To select images that would improve the representativeness of the dataset, we design a utility function that evaluates two aspects. The first one is if the new image is from underrepresented regions. And the second one is if the new image contains concepts that lead to the misclassification. Suppose an image of class C is misclassified as class C bar. In our example, class C is black tern and class C bar is white-breasted nuthatch. And let's consider three new images, X1, X2, and X3 we obtained from an external image repository. The first aspect we consider when assessing the utility is if the new image is from an underrepresented region. We say that a new image is from an underrepresented region if it contains visual features of the class C, but the model's confidence that the new image belongs to a different class C bar is high. Such samples are more informative and adding them to the training data may help the model generalize better. If we go back to our example, we can consider X1, X2, and X3 are placed as shown here. And X1, which is an image of a juvenile black tern, gets a higher beta value compared to X2 and X3, as it looks similar to black tern class, but the model misclassifies it into white-breasted nuthatch. Further, the new image should not only possess features of the class C, but also contains specific concepts that cause the model to make misclassifications. Adding images with these specific concepts will help the model to better differentiate between classes. Therefore, using an explanation method, we derive the set of concepts cause misclassification. Suppose we use a brace with explanations from CCNN. For each image of class C that CCNN misclassifies into class C bar, we obtain the set of concepts contributed for the model decision. Then we select top R concepts that have contributed for the highest number of misclassifications of class C. And this set, in our example, this set contains concepts of white breast and white belly. Then using gap layer output of CCNN for each of the identified concept, we calculate the degree of match between visual features in the new image and the identified concept set. The images with higher underrepresentation score and higher possibility to contain concepts used for misclassification will get the higher utility score, and those will be added to the original dataset for augmentation. Augmenting training dataset with these samples will increase the representativeness of the dataset. Note that the derivation of the concept set and cause for misclassification and the delta function depends on the explanation method. Brace can use any explanation, any concept-based explanation from post-hoc method or from inherently interpretable models. In this thesis, in addition to CCNN, I have explained how we can use GradCam with Brace. Next, let's move into performance evaluation. We use three datasets in our performance study. We conduct two types of comparative studies. In the first one, we compare the proposed approach with a state-of-the-art data augmentation method. In the second set of experiments, we compare our proposed approach with different sample selection methods. This graph shows the performance comparison of data augmentation methods when explanations from CCNN and from GradCam are used. We observe that Brace augmented datasets have achieved the highest accuracy across all the datasets. This graph shows the performance comparison of sample selection methods when explanations from CCNN and GradCam are used. Here also, we observe that Brace augmented datasets consistently achieves the highest accuracy. The improvement is bigger in cub families where there are more underrepresented regions. Here we visualize the sample selected for one class in subfamilies dataset where the original model performs poorly. We can observe that sample selected by Brace is the most similar to the images in the missing subcategories. This gives us the assurance that Brace is able to select samples from underrepresented regions and improve the representativeness of the dataset, leading to higher performance. In contrast, when use random, coset, or LLOS, they may select out of distribution images. On the other hand, confidence selects images which are similar to the original dataset. A representative dataset facilitates learning of more generalizable features. As a result, a classifier that is trained on such a representative dataset is able to recognize a wide variety of instances of a class, even when some of these variations were not part of the training data for that class. We demonstrate this generalizability of Brace in this experiment. We use a model trained on cub families and test it on a subset of NA birds dataset. This subset consists of classes that are found in cub families, but these classes have a wide variety of subcategories that may or may not be present in the cub families dataset. Also, for a model trained on Tiny ImageNet, we test it on a subset of images from ImageNet version 2. Again, this subset consists of classes that are found in Tiny ImageNet. However, it contains many variations that may not be present in the original Tiny ImageNet dataset. Table shows that Brace achieves the highest accuracy, confirming that Brace enables classifiers to learn features that are generalizable and can handle more diverse images. In summary, in the final work, we propose a framework that utilizes concept-based explanations to automatically augment the dataset with new images covering underrepresented regions to improve the model performance. The proposed framework enables models to learn features that are generalizable. As limitations, we need text descriptions for each image in order to train Flex and CCNN. Since these text descriptions are not available for some standard datasets such as ImageNet and Cypher10, we couldn't test our methods on those datasets. Also, architectural changes and regularizations we introduced to maintain interpretability of CCNN may reduce the classification accuracy. Please note that when the architecture is same, CCNN performs better than its counter black box model. However, CCNN cannot employ nonlinear or complex image aggregation methods, and therefore it can sometimes have a lower performance. Finally, if the external image repository does not contain diverse images, the performance of Brace may be adversely affected. For example, Brace may have less improvement for some domains such as healthcare, where there are less freely available images. As future work, we can think of many interesting directions. The first one is to reduce or eliminate dependency on text descriptions to generate linguistic explanations. In our thesis, we have already shown that CCNN and Flex can be trained using descriptions for only subset of images. However, it would be interesting to do more research on to see whether we can reduce this dependency more. For example, we can explore using class descriptions for all the images of a class. These class descriptions are noisy, and we have to come up with some method to eliminate these problems occur due to that. Also, another possible approach is to generate linguistic explanations for DNNs that use multimodal data. I didn't discuss all the technical details. However, all the work that I described here have been published in different conferences, and you can find the respective papers. Also, I have made publicly available the code related to all the work, so you can check on those and try for yourself. Thank you very much.